Two very important water quality parameters are total inorganic carbon and total organic carbon. The sum of these two equals the total carbon in the water. Carbon is a relatively abundant material on Earth, and it's the basic atom for life as we know it. Organic carbon comes from this life, including plants, animals, and microbes. Total organic carbon, while a fairly broad measurement, is a good indicator of water quality. Water that is heavily impacted by decaying plants, for example, will have a high total organic carbon concentration. A measurement of high TOC can indicate that there may be issues with several water treatment processes, including the formation of disinfection byproducts and total organic carbon adsorbing to sorbents like activated carbon rather than the chemical that the process was designed to remove. Meanwhile, inorganic carbon is directly related to alkalinity, the ability of a water to resist changes in pH. Let's recall the alkalinity equation and see some of the similarities between it and the equation for total inorganic carbon. So here, for the second equation, you might also see total carbonate used instead of total inorganic carbon. They would mean the same thing. You can see the overlap here between these two equations. Both bicarbonate and carbonate contribute to them. In aquatic samples, carbonate species that make up TOC can come from the atmosphere, CO2 gas, and rocks like calcium carbonate, which is the primary component of limestone. The carbonate cycle is also very important for global warming. Oceans are a large sink for carbon dioxide in the atmosphere. Carbon dioxide dissolves in the oceans and is converted to bicarbonate and carbonate. Then the carbonate can be incorporated into inorganic compounds like calcium carbonate, for example, by corals. For much of the Earth's history, the atmosphere and the oceans have been in equilibrium. However, the rapid increase in carbon dioxide emissions by humans over the last 100 or so years has disrupted this equilibrium, and the oceans can't absorb carbon dioxide as quickly as it is added to the atmosphere by humans. So this is very important for climate change, as the Earth can't fully utilize one of its largest carbon sinks. So if you want to learn more about inorganic carbon, oceans, and climate change, I've put a link to an article from ACS, the American Chemical Society, with more details in the description. So measuring organic carbon and inorganic carbon is relatively simple. Especially in the case of organic carbon, the measurement is much easier than measuring a number of individual target compounds that you may or may not actually be in your sample. So in a given situation, maybe you do find that your sample is high in TOC, and then you might decide to do further, more expensive analysis to determine what those compounds are exactly. Additionally, you might be working in a controlled laboratory environment where you know that your sample only has one type of organic compound. Then you could use TOC to determine the amount of that material, which might be less expensive and less tedious than other methods. So to measure inorganic carbon, generally you would increase the acidity of your solution by adding a non-oxidizing acid that isn't going to react with the organic carbon. The acid will lower the pH, effectively converting the inorganic carbon, that is the carbonate and bicarbonate, to carbonic acid and to CO2 gas. Then you bubble inert gas through the sample, and the CO2 gas will come off the sample, and you can measure that with a detector. So this whole process of adding acid to your sample to convert all of the inorganic carbon to CO2 is governed by acid-base equilibrium, and that's the topic of this video. So by the end of this video, you should be able to define total carbon, total inorganic carbon, and total organic carbon. You should also be able to use acid-base equilibrium constants to determine the relative concentrations of acids and conjugate bases given pH and vice versa. And you should be able to sketch a graph that shows the speciation of different acids acids and bases given the pKa's. So let's return to our example. So when you measure TOC, once all of the TIC is converted to carbon dioxide gas, then you would oxidize your organic carbon, and this also would end up converting it to CO2 gas, and you can measure that with a detector. So for the sake of this video, I'm only going to focus on the inorganic carbon and how all of the inorganic carbon can be off-gassed when you lower the pH of your water sample. So again, this process is due to acid-base equilibrium between the carbonate species. So carbonate species, or inorganic carbon, include carbonic acid, which is H2CO3, bicarbonate, HCO3-, and carbonate, CO3-2-. All of these species are related by the following acid-base equilibrium equations. So I want to make several points regarding these equations. In the first one, H2CO3 star, the star means that carbon dioxide that's dissolved in water is included with the carbonic acid. In the first equation, H2CO3 star is going to be the acid, and then bicarbonate, HCO3- will be the conjugate base. In the second equation, HCO3- bicarbonate is the acid, and then carbonate is the conjugate base. So depending on which equation you're talking about, bicarbonate might be either the acid or the conjugate base. Two equilibriums exist here. We have two acid dissociation constants, two pKa's, 1 and 2, and we can write two different equilibrium equations given the information that I have here. So what if we had the carbon dioxide concentration in the atmosphere and we had a water sample that was in equilibrium with that carbon dioxide? How would we go about doing this problem, right, to get the total inorganic carbon of the sample? So the first thing we need to do is we need to calculate the carbonic acid concentration in the aqueous phase given the carbon dioxide concentration in the vapor phase. So this is going back to the video that I previously posted on Henry's law. So let's start here. And let's say our atmospheric concentration is 410 parts per million carbon dioxide. That's what the average concentration is, or was, in 2019. So we'll use the following chemical equilibrium equation. We have carbon dioxide gas dissolving in water to form H2CO3 star, and we have a Henry's law constant Kh for this equation. So notice how this chemical equilibrium equation also has this star in it. So that means that it includes both dissolved CO2 and H2CO3. So we'll rearrange. Well, we'll write this down. So we've got Kh equals H2CO3 star divided by the partial pressure of CO2, and that is our Henry's law constant. We need the partial pressure of CO2. So what we can do is we can convert that concentration in parts per million to a partial pressure. So I've taken 410 moles CO2 per million moles of everything else. And then I remember that mole fractions equal pressure fractions for gases. So that is my pressure fraction. And if I work that out, it's 4.1 times 10 to the negative 4 atmospheres. So I can just plug that into the equation, multiply it by the Henry's law constant, and I get a carbonic acid concentration of 1.39 times 10 to the negative 5th moles per liter. So for the rest of this, I'm going to assume that my sample has a pH of 6. Okay, so I'll look at this equation here for H2CO3 star, and I see a pKa of 6.35. So I need to get the equilibrium constant from that pKa. pK is very similar to pH, so we do it the same way. So our Ka1 is going to be 10 to the negative pKa, or in this case 10 to the negative 6.35. That is going to equal the product of the species on the right-hand side of the equation divided by our species on the left-hand side of the equation. All I need to do is rearrange for bicarbonate and plug and chug. The H plus concentration I can get from our pH. So that H plus concentration will be 10 to the negative pH, or 10 to the negative 6 moles per liter. And I end up with 6.21 times 10 to the negative 6 moles per liter. Okay, finally, I'm going to use the second acid dissociation constant to calculate the carbonate concentration. So you've got two different equilibrium equations, two pKa's, and you do two separate equations. So I've set this up exactly the same way as previous. I've got our Ka equals 10 to the negative pKa, or 10.33. And then I've rearranged for carbonate and solved it for 2.9 times 10 to the negative 10 moles per liter. So I'm interested in our TIC, inorganic carbon, in this sample that has all of its inorganic carbon from the atmosphere. So our total inorganic carbon is going to be the sum of our carbonic acid, H2CO3, bicarbonate, HCO3-, and carbonate, CO3-2-. And I add all of these together, and I end up with 2.01 times 10 to the negative 5th moles per liter. So if I were to look at this and look at each of the components, I can see that at our pH 6, the TIC is primarily made up of carbonic acid and bicarbonate, with just a very, very tiny amount of carbonate. Okay, so if I used a TOC-TIC analyzer to measure the sample, the machine should say that my TIC is 2 times 10 to the negative 5th moles per liter. You could also use a pretty similar method to calculate alkalinity of the water in equilibrium with the atmosphere, and I do encourage you to do that. So it still might not be clear how this machine converts all of the total inorganic carbon to CO2 gas. For that, what we're going to do is look at the acid-base equilibrium equations we used above. What we can do is we'll use those two equations along with the equation for TIC to derive these three following equations. These are bicarbonate, carbonate, and carbonic acid as a function of the total inorganic carbon, the pH, or H plus concentration, and the pKa's. If you take these equations, you can plot the concentrations of each carbonate species as a function of pH. So I've got my Excel spreadsheet here, and I do encourage you, you can make your own Excel spreadsheet like this, check your numbers with mine, and then you can use that spreadsheet for a number of acids just by changing the pKa's. It'll work for any diprotic acid. So here I have the three concentrations of carbonate species, and I have actually plotted them as a fraction of the total inorganic carbon. So that's on the y-axis, and then I have pH on the x-axis. So first I want to point out a few things. So you can see that at every pH except for two of them, one carbonate species dominates. At the very low pHs, carbonic acid is going to dominate, and then at the high pH, the completely deprotonated species, carbonate, dominates. In between that species with only one proton, bicarbonate is going to dominate. You can also see that these three lines cross at 2 points. These are the points where the pH equals the pKa's, 6.3 and 10.3. Thus, you really could sketch this kind of graph for any acid-base system if you were given the pKa's. Depending on if they're a monoprotic, diprotic, or triprotic acid, your graph will look a little different. This is how it will look for a diprotic acid, because you have 2 protons that can be removed and 3 species present. You can also compare the pH of your system with the pKa's to determine which species will dominate. For example, in the system, if I told you the pH was 11, you would know that carbonate dominates because the pH is greater than the second pKa 10.3. If I told you the pH was 2, you would know that carbonic acid dominates because the pH is less than the first pKa 6.3. So let's go back to our TIC example. We took our sample, we determined that the pH was 6, which is very close to the first pKa of 6.3. That's why we calculated that we had primarily carbonic acid and bicarbonate in our sample with very little carbonate. And you can see this on this graph. If we lower the pH even more, you can see that we'll push all of the carbonate species to the form of H2CO3 star, which includes CO2 gas, and we can bubble that off and measure it with our detector to measure the total TIC. After you've done that in a sample, you can go ahead and measure the TOC, the organic carbon, by oxidizing that to CO2 as well. So now that you've seen this video, you should be able to define total carbon, total inorganic carbon, and total organic carbon. You should be able to use acid-base equilibrium constants to determine the relative concentrations of acids and conjugate bases given pH and vice versa. If I gave you the concentrations of an acid and conjugate base, you should be able to tell me the pH. You should also be able to sketch a graph like I showed you, showing the speciation of a weak acid for any system if I give you the pKa's. And with that concludes my video, and I welcome you to go make your own Excel graph and calculate the alkalinity for the carbonate system that we talked about.